In this segment, we'll introduce a subclass or derived class of vector from the prior segment, and we'll look at overriding methods, private versus protected access, and other inheritance-related concepts. Now, our simulation will often need vectors that have some margin of error when comparing for equality. In particular, if we want to know if two simulated entities are in the same place in the simulation, then we should compare their locations, which I've drawn up here as a couple of example black vectors. We should compare them within some range, the circle around them, so that if they're close enough, then their two location vectors are considered equal. So what we'll do is create a margin vector class right over here. And this one follows an approximate rule for equality checking. And we'll use it when we want vectors with a margin of error. Now, our margin vector should behave in other respects like the existing vector class from the prior segment, including having all the members and methods of vector. All we want to change is the equals method. So we'll derive margin vector from vector. Now, you should already have seen derivation or inheritance in prior courses, but let's review the major ideas using the example margin vector class here. Margin vector's first line announces that it extends vector, as you can see there. Now, this is the Java syntax for declaring that margin vector inherits from or derives from vector. And it makes margin vector a derived class or a subclass of vector. And it makes vector, in turn, a superclass or base class of margin vector. I'll generally use the terms subclass and superclass, but will now and then switch to derived class and base class. The two pairs of terms are synonymous, and you should be comfortable with both. Now, this relationship between the classes has a number of implications, but the most obvious is that margin vector automatically has all the same members and methods as vector. It inherits them all from vector. In fact, declaring margin vector, like I show in the notes, with nothing but the empty curly braces, if I were to take, in other words, all of this away, leaving just the header and empty curly braces, with no members or methods declared for margin vector at all, that would make margin vector effectively a duplicate class of vector, usable in exactly the same way as vector, with minus, plus, xy, and all the other vector members and methods being automatically a part of margin vector. Now, there are actually a few rare cases where inheritance is used in just this way, but normally we add declarations of members and or methods for the subclass. These, however, are in addition to, or in some cases in replacement of, the members and methods already inherited from the superclass. Margin vector, for instance, adds a new static member datum, margin, and two static methods, set margin, get margin, to set it or to get it. And we'll be talking more about those in a later segment. In general, a subclass may add as many additional members or methods, static or non-static, as it desires, extending upon or augmenting what it gets from its superclass. Now, a couple of diagrams may be useful here. First, the UML diagramming system that we'll use in this course includes a way to diagrammatically represent inheritance, with the superclass above and the subclass below, and a triangle terminated kind of arrow-like line leading from the subclass up to the superclass. And derived classes are typically drawn below their base class in any object-oriented diagramming system, which is why they're called subclasses, even though they add members or methods to their base class and they take nothing away. Now, this class diagram has a problem. It invites a misunderstanding regarding the nature of the subclass objects themselves. A subclass object, a margin vector object, for instance, is not two boxes. That describes the class relationship, not the resultant object structure. A subclass object looks like this diagram here. It's a single block of memory with the top half here comprising the superclass member data and methods. The methods, at least abstractly, the reality of methods still applies here. And then there's an additional bottom half, and it adds extra members and methods declared by the subclass. Now, in some cases, a derived class simply adds more content, but more often, a derived class also redefines or overrides, again those are synonymous terms, redefines or overrides methods from its base class. The equals method in margin vector is a good example. Margin vector inherited an equals method from vector, but the base class equals won't suffice for margin vector, which needs an inexact equality check. So margin vector defines its own equals with parameters and return type identical to the base class version, but with logic that computes a difference vector, thus the minus there, between the context object and other, and then takes the length of that and checks that it's less than margin. So this version of equals thus returns true if the two margin vectors are within margin of one another. Now, a subclass may override or redefine any non-constructor method of the superclass, and for the subclass objects, the redefined methods will be called instead of the superclass version. Redefinition is often used to create a subclass that behaves much like its superclass, but tweaks the superclass behavior for certain methods. Now, redefining a method requires an exact match of the superclass method's name, parameter types, and return type. It's easy to mess this up, in particular getting the parameter types wrong. And if you do, there's no compiler error. Instead, you get both the superclass method and the subclass version, which is considered an added method and does not override or replace the superclass version. Which one gets called depends on whether the parameters in the call match one version or the other. Now, to avoid this problem, always add the Java annotation @override before any method you override. This tells the compiler, I mean to override a method in the superclass, and you'll get a compile error if you don't match the name and parameters exactly. And here's an in-lecture question for you then. What if we want margin vector to have a slightly different two-string result, saying, putting a tilde, let's say, before the dimensions to show that they're approximate. So we'd like, in other words, for it to return something like this. It's in the notes as well, for the result of two-string. Now, how do we do that? And they're returning from a pause there. Well, obviously what we need to do then is redefine the two-string method. And it might look something, see if I can fit it in here like this. It's, again, also in the notes. So we'd do something like that. An add override, public string, two-string, and return a string that, if you put it all together, will look like the one that we wanted down here. And note, by the way, that we can use x and y in our two-string method because they are members of margin vector, having been inherited from vector. But is it always true that we can use the members and methods of the base class? Now, I'll clean up the diagram a little here, and then let's try another change. Calling length and minus in equals is rather inefficient. We could just directly compute the distance between the two margin vectors in equals by summing their squared x and y differences. If we want to be really clever, we don't even need to do a square root. We'll just compare the squared distance with margin squared. And if the squared distance is less than the squared margin, then the distance itself is less than the margin. Let's try it. And I'm going to do it in Eclipse here so we can actually see the result. I'm going to take my margin vector equals right here, and I'm going to replace what it currently has with this instead. return the square of this dot x minus other dot x plus the square of this dot y minus other dot y, and compare that to the square of margin. If it's less, we'll return true. But as you can see, Eclipse is already not happy with me. I don't know if it's legible in the diagram or not, but these two little error indicators are saying the same basic thing in each case. And what they're telling me is that the method square from the type vector is not visible. We're not allowed to call square. Huh? We inherited square, right? It's part of margin vector by right of being a subclass of vector. Yeah, but square is private in vector. Now, this means that while it is officially part of any vector subclass, including a margin vector, the subclass cannot call it. Only code in the base class vector can. To make it accessible to subclasses, it needs to be protected or public. So let's change it, and now the method will compile. And go back over to margin vector, and our errors go away. Now, let's talk a little more about this, because it seems pretty maddening. A subclass can actually have methods or members inherited from its base class, but be unable to access them due to private declaration. It's like Daddy is saying, everything I have is yours, but I won't give you the keys to the car. Why would you do this? Well, stretching the parental analogy a little further, if a minor inherits property, they own it, but are often not allowed to control it because they're not sufficiently responsible yet. And by the same token, there are cases where a subclass, or more precisely its developer, is not trusted to directly modify superclass inherited property even though it owns it. The subclass code must instead access superclass members only via public methods like anyone else. The most notable example of this are base classes in object-oriented libraries. Object-oriented libraries commonly provide base classes that offer standard behavior, which a developer can customize or extend by deriving classes from the base class. If a GUI library, for instance, provides a window class with standard behavior, a developer might derive a class myWindow from it and redefine, say, a draw method from the window superclass to change how myWindow does drawing, but to leave all the other members and methods of window unchanged. But the developer using the library might be anyone, and the member data of window may be complex and need to be updated in just the right way and may even change in the future. The library author doesn't trust just any developer to do that correctly, so she or he would not make window data accessible to myWindow. They'd keep it private, and though they'd be part of a myWindow object, the added or overridden myWindow code would not get direct access to that private data. Now, going back to our earlier example here with the redone equals method, if x and y were private in vector, but square was still only protected, how would you write the overridden margin vector dot equals method? It can still be done, it's just a bit more cumbersome. So here's Eclipse back again, and we're going to make these guys private because we don't trust our derived class author. And as a result, the code in margin vector is going to pick up errors saying the field vector.x is not visible, and ditto for vector.y. So what do we do to repair that right here in the margin vector code? Coming back from a pause there, well, the answer would be to use getX, of course, which is public and available, to fetch our own member data. And that clears the error on the first line, and a similar use of getY here and here would clear it on the second line. Now, this is a major decision that one makes when designing a potential base class. Do you declare non-public members and methods protected or private? Do you trust your children or don't you? Do you put developers of your subclasses through the irritating step of having to call getX just to get the value of one of their own member data, or do you allow them to or do you trust them to have direct access? Generally, protected access is used in cases where the subclasses will be written by members of the same small team, not by unknown third parties or by members of a larger team where communication about design is not as easy. In the small team, we trust those writing the subclasses to be aware of the superclass design and to make proper direct use of superclass members. In most of the course examples, we'll use protected access, but at least one of the LMQs will require you to use private access.